Hello and welcome to today's lesson on momentum. Our learning objectives are to define momentum, describe examples of momentum in collisions, and recall and apply equations for momentum. To begin with, we have 5 different sports balls, and what I'd like you to do is put them in order from the most difficult to stop to the least difficult to stop, assuming that they're travelling at a typical speed for their appropriate sport. Pause the video now while you write in your books which order you think they would go in. We'll come back to that in a few minutes, but for now we're looking at momentum, and one way of thinking about momentum is how difficult it is to stop something or to get it moving. Momentum depends on 2 things. One is the mass of the object that's moving, and the other is its velocity, how quickly it's moving. Now, momentum is a vector quantity. Its direction depends on the velocity that the object's moving in. When you do calculations involving momentum, you do need to take into account its direction. The equation for calculating momentum is momentum in kilogram meters per second is equal to mass in kilograms times speed in meters per second. You do need to recall and apply this equation. Pause the video here while you copy that into your books. We're now going to use that equation to find out how much momentum a rugby player has. In this example, our rugby player has a mass of 120 kilograms and a velocity of 5 meters per second. To find his momentum, we need to times his mass by his velocity, so 120 times 5, which would give us a total momentum of 600 kilogram meters per second. Now, using that equation, I would like you to find the momentum for each of these 5 sports balls. Remember, momentum is the mass in kilograms times the velocity in meters per second. Pause the video now while you do those calculations. So the momentum of the bowling ball would be 38 kilogram meters per second, the cricket ball 7.2 kilogram meters per second, the squash ball 2.73 kilogram meters per second, the golf ball 4.7 kilogram meters per second, and the football 13.33 kilogram meters per second. Once you've finished marking the last question, you can look at how your answers at the start of this lesson for which is the most difficult ball to stop compare with the true values as you've calculated. The most difficult ball to stop would be the bowling ball, followed by the football, then the cricket ball, the golf ball, and finally the squash ball. In any situation, momentum is always conserved. So when objects collide together or they explode apart, momentum will always be the same before the collision and after the collision. This can be very important when we're doing calculations. Here we have a small red ball that's about to collide with a blue ball. Now, the total momentum of the red ball and the blue ball is the momentum of the red ball, 10 times 2 for 20 kilogram meters per second, plus the momentum of the blue ball, 2 times 5, 10 kilogram meters per second. So the total is 30 kilogram meters per second. The total momentum of the system before they collide is 30 kilogram meters per second. Because of conservation of momentum, we know that the total momentum after the collision is going to equal the total momentum before the collision, so 30 kilogram meters per second. Now, if you look at the red ball, that has a momentum of 2 times 5, 10 kilogram meters per second, which leaves 20 kilogram meters per second for the blue ball. If its mass is 5 kilograms and its momentum is 20 kilogram meters per second, then we can find its velocity fairly simply. By dividing 20 kilogram meters per second by 5 kilograms, we find the velocity is 4 meters per second. So the blue ball would be travelling at 4 meters per second after the collision. The law of conservation of momentum states that the total momentum before a collision equals the total momentum after a collision. Pause the video here and copy down the law of conservation of momentum into your books. The momentum of two skaters who are stationary before they push apart is 0. If they move away from each other with momentum that is equal in size but opposite in direction, the total momentum afterwards is also 0. This is called an explosion. Explosion is a term used to describe a wide variety of situations, but in each case the objects are stationary before the explosion and therefore have 0 momentum. As a result, after the explosion, the total momentum for all of the constituent parts has to add up to 0. Now we're going to look at some collisions. In an elastic collision, the total kinetic energy before the collision is the same as the total kinetic energy after the collision. No energy is transferred to any other energy stores. As an example, on a snooker table, if a white ball is rolling along and it hits a stationary red ball, the white ball then stops. You would expect the red ball to move off with the same velocity as the white ball had. In an inelastic collision, some energy is transferred from the kinetic store to other stores. Normally, this is the thermal store of the surroundings. In real life, almost no collision is perfectly elastic, as some energy is transferred to the thermal store of the surroundings as sound. You can hear this energy transfer when snooker balls collide. Trolley A of mass 180 grams is moving at a velocity of 4 meters per second towards trolley B, which is stationary and has a mass of 120 grams. Trolley A then collides with trolley B. Find the speed of trolley B after the collision. Assume in the first case that when trolley A hits trolley A comes to a complete stop and trolley B moves off with all the momentum in the system. In the second situation, assume the two trolleys come together when they collide and are joined and move off as one. Pause the video now and work out the answer to both those two questions. For the first question, all you have to do is find out the total momentum in the system before the collision, which is the mass of trolley A times the speed of trolley A, 180 times 4, and that will be equal to the mass of trolley B times the velocity of trolley B after the collision. If you divide the total momentum by the mass of trolley B, that will give you the final velocity of 6 meters per second. In the second example, you start off exactly the same, finding the total momentum in the system by timesing the velocity by the mass for trolley A, and then you need to divide that by the total mass of trolley A and trolley B. That will give you a total speed of 2.4 meters per second. A squash ball of mass 24 grams moves towards a wall with a velocity of 12 meters per second. It strikes the wall, remaining in contact with the wall for 0.02 seconds before bouncing back into the squash court with a speed of 12 meters per second. First of all, find the momentum of the squash ball as it moves towards the wall. Secondly, find the momentum of the ball after it's hit the wall. Remember, it will be travelling in the opposite direction, so its momentum should have a minus sign. And finally, find the change in momentum of the ball. Pause the video here while you find the answer to those three questions. For the first part of the question, the mass is changed into kilograms, so 0.024 kilograms, and then times by the velocity of 16 meters per second, giving a momentum of 0.384 kilogram meters per second. For the second part of the question, the mass again is 0.024 kilograms, and this time we're timesing it by the velocity. Notice the minus sign to show it's going in the opposite direction, so minus 12 meters per second, giving a momentum in the opposite direction of 0.288 kilogram meters per second. The difference between the two values is 0.0672 kilogram meters per second. Write down the principle of conservation of momentum in your books. Don't forget to pause the video while you're doing that. The total momentum before a collision is equal to the total momentum after a collision. This principle also applies to explosions. Explain the difference between elastic and inelastic collisions, and explain why perfectly elastic collisions are not normally seen in nature. Pause the video now while you write that in your books. Kinetic energy is conserved in elastic collisions, but in inelastic collisions it is not. This is why it's very rare to see elastic collisions in nature, because some energy is normally transferred from the kinetic store to the thermal store of the surroundings. Well, that brings us to the end of today's lesson. I hope you found that useful, and thank you very much.